Again, good morning and welcome to week 10. We are in the second half of the course. I think we still have a long way before we can call it basically we're there. I think about a week behind in the schedule or something like that. Anyway, today is we're finishing the part that has to do with the chemical reactions basically and how they proceed. And then we still have another chapter for basically the types of chemical reactions. That's the next chapter. And that's kind of big chapter in terms of basically slides, but you will see it's not really big in terms of content. Uh, then we will finish this section with the organic chemistry. And that should basically put us somewhere in the middle of next week. I'm not sure. I don't think that we will have the exam next week. It's going to be the week after. It's going to be a week before the week of Thanksgiving. After that, we're going to touch a little bit with the earth science, basically geology, and astronomy. There is some commonality between the two in a sense that once we talk about once we talk about astronomy, we will discuss things that have to do with the chemistry and the geology of planets. So at that point, we will save a little bit of time when we do that, and except when we talk about also stars, and that also involves stuff from chapter 13, namely nuclear reactions and things of this nature. So when we get into astronomy, I think it's going to be the summary of a lot of concepts. As a matter of fact, you're seeing it right now when we're doing chemistry because we're talking energy, we're talking about electrostatic forces and things like that. So things as they build up down the road, we will build on prior concepts that we have discussed. Okay, so let's finish this stuff unless you guys have a question. No. So I'm gonna get into chapter 17. So again, it's how chemical reacts. There are a few concepts that we will need to talk about, and that is chemical equations and how they are represented. And they rely on an idea that is somewhat accurate. I wouldn't say 100% accurate. And in light of what we've learned in chapter 13, especially about nuclear reactions, and that is the idea of conservation of mass. It's approximately accurate. So the conservation of mass, because chemical reactions involve exchange of energy, whether they give energy or they take energy. In a sense, if they give energy, that is actually a decrease of a tiny, tiny, tiny fraction of mass that is negligible in a sense of chemical reactions, and that is translated in the form of energy. In the case of when chemical reactions require energy, that is actually an increase in mass, but it's a very, 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 very small quantity that is negligible in chemical reactions. So to this order of approximation, the conservation of mass is actually is very good in chemistry, so that we're going to assume that it's accurate in this sense, okay? Uh, we're going to talk about chemical reaction rates and how we can expedite them and what makes them slower than others. So that's basically one thing. We're going to talk about catalysts, and how basically chemical reactions can be enhanced or can happen all together just in presence of certain conditions that have to do with temperature, other elements or concentration, other things like that. Then we're going to delve into a little bit of a quantitative approach into trying to measure the chemical reactions and see whether or not we're going to get energy out of them in the form of kinetic energy or in the form of radiation, basically in the form of electromagnetic radiation. Or we're going to actually require temperature or heat in general for them to occur. In a sense, they require energy. So those are the two things we're going to do. And at the end, we're going to touch base with the fact that no process in chemistry is actually feasible on its own unless the entropy allows it. If that is the case, then the system will evolve toward a higher level of entropy, which is natural for any phenomenon. As a matter of fact, when we talked about thermodynamics, we said that this science basically oversees everything in all branches of science, not just basically chemistry, also in physics, everywhere else. So if a chemical reaction is not possible then to occur on its own, then you might need to interject in it a quantity that apparently may seem to lower the entropy of the system in question, but overall it still obeys to the laws of thermodynamics in a sense. The entropy of the universe taken with the account of that system and its environment, still the law of entropy still works in this case. So that is actually a concept that facilitates this idea in here. For some reason, we only have few people today, and I know the time clock is going to change next week. So people who tend to basically stay in bed a little longer, so they can stay longer next week, and hopefully we will be more in the classroom. Is my understanding correct with this time change? Are we going to have the class later in the day, or is it going to be earlier and we're going to have fewer people? I'm always not sure about this until it happens. Does
We're
anybody know?
supposed to fall back.
So what that means that we will have an extra hour so that to catch up with the sleepers, or are we going to lose some of you, the
Yes.
people? Okay,
No, you
so
get an extra hour, but it's only for one day.
sorry for 1 day? No, for 2 days
No,
for
I
us.
mean for people to, get used to it.
Okay, okay. So we will gain more people hopefully starting from next week because I noticed that with time that people started to not show as many as past. I'm glad also that people are catching up still with the lectures online because I post the videos in the discussion sessions and they come in and basically join the discussion later on. Then I also monitor that through Google because I see how many people are actually looking at these videos. Okay. Anyway, so again, this is basically in a nutshell what this chapter is all about. So here I have a chemical reaction. I have basically hydrogen combining with oxygen to give me water in this case, okay? And chemical reaction has these symbols in it. First of all, the element itself in here, H for hydrogen, O for oxygen, and H2O for the compound they form, which is water in this case. That's one thing. The other thing also we usually represent in this case, in this type of equation, whether the reactants or the products, we also, at least if we want to be detailed about it, the state, the phase of this reactants and products. And it's in parentheses in this case, it's the letter G stands for gas, S stands for solid, and L stands for liquid. So this is a chemical reaction that happens in the gas form and it's going to give me vapor basically of H2O. Apparently it's going to condensate later on, becomes liquid water. But that's basically the chemical reaction as it's written symbolically. Also, there are numbers attached to it, appended to it before this symbols, and namely the how many, if you wish, atoms are or molecules in this case are connecting with one another. I would need two molecules of H2, which is in this case hydrogen gas, combining them with one molecule of oxygen gas, O2, to get me two basically molecules of water vapor in this case, H2O. Obviously, if you double the numbers, it's going to double. If you have 6 times 10 to the power 23 of them, it's going to have this many. 2 times 6 to the power 23 plus 1 times 6 10 to the power 23 plus give me at the end 2 times 6 times 10 to the power 23. And 6 times 10 to the power 23 is the Avogadro number. In other words, as these numbers increase, they are proportionally in there going with one another. So the number in there before the symbols represent the actual molecules, okay? And then they go proportionally everywhere, okay? As I said before, the law of conservation of mass in this case states that no atoms are gained or lost in a reaction, in a chemical reaction. Remember, we're not declaring. I mean, I probably will state that because I've dealt a lot with nuclear reactions. So sometimes I said that, but these are chemical reactions. So in this case, if you start with the, I don't know, for example, specific atom, hydrogen, we're not going to get into a different kind of hydrogen at the end or a different kind of helium all of a sudden or something like that. But the point being in here is that I started with how many hydrogen atoms in this chemical reaction? I have one, two, three, four. That is before they react with the oxygen atoms, in this case, in the water, in the oxygen molecule. So in this case, I still have in the water two, and this one has two. So I ended up with four still. So in this case, what I'm saying is the conservation of mass is really the conservation of the number of atoms of individual, basically, components. Same thing, oxygen in this case, I started with two, and in each of these two water molecules, I have one, so I still have two of them. So this is the conservation in this sense. It works beautifully. There is no argument with it, okay? And it's the basis for every chemical reaction. So the number of times appears before the arrow must be equal to the number of times appears after the arrow. That is what this means, that if I calculate in here the number of hydrogen atoms, they will be the same number afterwards. They may have rearranged themselves. They used to be in a certain configuration, but now they're in different configuration. That's what chemistry is all about, but their number stays the same, okay? So here is an example. I have six molecules in this case, six atoms, I'm sorry, okay? They were combining themselves into three, grouped together into two groups. Now they ended up being in three groups of two, but their number should be the same. So the question is, how many atoms are represented by the following schematic for a chemical reaction? In this case, I have six. Six before is equal to six before, after. The six before were grouping themselves in two groups of three. After the chemical reaction, they rearranged themselves and they redistributed themselves and they became three groups of two. It's still six before and six after. So that's in a nutshell what a chemical reaction is. Again, the answer is six to the question. Okay. And here are the reactants, the six of them. Now they're all of a sudden basically broken, breaking their bonding in the way that they were initially. So the three and the three now, they are no longer together. They are separated and they continue rearranging one another until at the end, they come into this configuration, okay? And now this is the product, which is the same number of atoms before and after. So this is the premise of chemistry. This is the basic idea of chemistry. So again, in compliance with, or at least based on the request of Sarah, so the basic, what is the basic premise or the basic principle of chemistry, chemical equations? Basic principle of chemical equations is the conservation, I'm going to put it in parentheses, of mass, actually the number of atoms, reactant atoms, equals the number of products atoms, or product atoms. Guys, so this is item one. Good? So again, we're going through the idea in detail. Here is another example. Is this equation balanced? It is balanced when I calculate, when I compute the number of reactants, okay? The atoms in the reactants, all of them. and see if they match the number of atoms in the products. If they do, then the equation is balanced. If they don't, then the equation is not balanced. Okay, so in this case, of course, this is symbolic. This is not an exact example in here. But if I look, for example, on this color, which looks to me like purplish thing in here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them. I need to find 14 of them on the other side. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What, did I miss one? I have 4 in here, and 4 in here. That's 8. And 4, that's 12. And 2, that's 14. Okay. So in terms of this kind of atom, I have the exact number, 14 to start with and 14 to end with. In terms of this greenish or this color, okay, I have 2 of them to begin with, and I also have 2 at the end. So we're good in terms of that. You are not balanced until every one of them is accounted for, okay? In terms of the blue one, I have 1 and 2, and then I have 1 and 2, 3 and 4. Is this balanced? What do you guys think? And in here I have oranges, 2 of them, and I don't see them in here. So Sarah thinks it's no. Rudy thinks it's no. It, I mean, the question may be confusing a little bit because I don't know the relationship of the blue ones to the orange ones. If they have the same, basically, atomic mass, if they are the same kind of atoms, except that they're rearranged differently, then in this case they are. Okay, because if I count them, the number of all of the atoms in here, if they're all protons, for example, it's the same number on the other side. But you're absolutely right, it's not balanced. If this have a different atomic mass than this one, then I have actually less blue ones to begin with, and I ended up with more, 2 extra. And for some reason, this 2 disappeared and became something else. Okay. So that is really, this question is kind of not clear in here. Okay. Does everybody understand what's going on in here or not? The confusion is about the blue and the orange. Unless you guys looking at them with the same color, because some people have different perceptions of colors. Okay. So the point in here, based on the principal idea, is that the number has to be the same. Here is another question. How many diatomic molecules are represented? This is very, very important in this reaction. This example, I'm sorry. How many of diatomic molecules are present in here? In other words, molecule that has only 2 atoms in it.
Do you have to count them up from both slides, from both boxes?
No, on the reactants. And the reactants, how many they are first? And then on the products, how many they are. You're right. So both of them, but we have to separate them with this arrow. How many in the products? Count them. The atoms with just 2, the molecules with just 2 atoms. Okay, Sherry thinks it's 2. Everybody now thinks it's 2. No, somebody else thinks it's D. It's 4. They are 1, 2. We're not counting the individual atoms, Rudy. We're counting the molecules now. Okay. So there are two of them. Do you see that? This is molecule one. This is molecule two. Okay, very good. Then what happened after the reaction? How many do we still have? One. So is this an issue now? Do you understand what I'm trying to say in here? Did I bring enough of these diatomic molecules, or did I bring more than I need? What do you guys think? Did I bring enough of these diatomic molecules, or did I bring not enough of that? More than what we need. So in this case, yes, there is kind of a waste in this case. So that's really something that we try to avoid when we're doing chemical reactions in this case. We just bring what we need in this case, okay? In order to say that you're really truly balanced, you have to have exactly the excess in this case is wasted. So you have to really know how many do you need from the reactants in order to produce as much as you need from the product. That's really the another point in here that you need to be aware of. Okay. Again, this is the point in here. This ended up being not reacting, as you can clearly see in this case. Now, we're checking to see if this chemical reaction is balanced. The only way to do that is to actually count each and every one of these atoms to see how many do you have before. Now, this is not as before, which is symbolic representation of the atoms. These are actual atoms. So how many carbons did I start with? Remember, in here I have to multiply by this number. I don't just count the number in here, okay? So yes, I have 1 in this methane of carbon, and there is a 1-to-1 correspondence. So I have 1 atom of carbon to start with. When I ended up the chemical reaction, I ended up with how many carbons? The carbon. So I started with 1, and after the chemical reaction, do I have a C in the second side? Okay, good. Thank you. I was worried for a second. So yeah, there is actually a carbon in it. I'm not talking about the molecules of methane. Yes, I don't have anything after that. But again, when we're tracking this number, we're tracking individual atoms in this case. So we started with 1 carbon atom inside this CH4. Now we still have 1 carbon in this CO2. It's true. So we're good in terms of carbon. In terms of hydrogen, we started with 4 hydrogens in this molecule times 1. So we have 4 to start with. Now we ended up with 2 hydrogen atoms in the water molecule. But how many water molecules do we have? We have 2 of them. So we have 4 at the end. So why are you saying 0, Sherry? I'm kind of confused. We had 4 to begin with, and we have 2 times 2, which is 4. Correct?
I was looking at the 1 CO2.
Okay. Okay, so the CO2, we don't have any hydrogen, so we don't worry about it. When we're counting this, we have to look at the entire side and compare it with the entire side. And we may even have presence of different molecules and different, different atoms and different molecules. So in this case, we're lucky in a sense, we only have H4 in here. So we only have 4 of them times 1. In this case, we're good because we have 2 times 2, which is 4. That's the next thing is the problem. 2 times 2, again, I have 2 atoms in each molecule of oxygen gas but I have two of them. So I have 2 times 2, which is 4. Now I have to look at the oxygen everywhere, not just in here. Same thing, I should have looked at it everywhere, but I was fortunate enough to find it in one place. And here I have in the water molecule, I have only one oxygen, but I have two water molecules. So 2 times 1 is 2, plus I have 2 oxygen atoms in each CO2 molecule, but I only have one of them. So total is still 4. So 4 before and 4 after. So this chemical reaction is balanced. Okay. Does this make sense to you guys? Yes. We have to tally each and every one of them to say it's balanced or not. Okay, very good. Okay, chemists need a way to express a mathematical equation, and again, this is basically the. So we go to the periodic table to give the mass of each element, and okay, here's the deal, and we saw it earlier when we were talking about that example with the two diatomic molecules. Okay, we know in that case that only one of them is actually needed, so one was gone to waste. So if we're doing this chemical reaction, for example, how many do I know exactly? I need 2 molecules of oxygen for each CH4, for each molecule of CH4. So that is basically the proportions. How much should I bring of O2 versus how much should I bring of CH4 if I want to produce, for example, 2 molecules of water? Okay. So that's the challenge in this case. Should I bring 100 grams of this guy and 100 grams of this guy, or 100 grams of CH4 and 200 grams of O2? That is the challenge. If I bring, for example, 100 grams of CH4, am I going to waste some of the oxygen when I put it on the other side, or am I going to waste some of the CH4 to put it on the other side? That's why we needed actually the Avogadro's number. Avogadro's number in this case is just a representation to tell me how many actual reactants are needed to react to produce the products you want. Okay. So instead of talking number of molecules, because we really don't deal with the single molecule or 2 or 3 of them, we decided on the Avogadro's number in here, and the Avogadro's number is how many molecules basically, or how many atoms, if we're talking about individual atoms, are in a gram mass that is represented by the atomic mass of that molecule or that atom. Okay, so that is basically how, by definition, the Avogadro's number is. From there on, we just talk about how many of this Avogadro's numbers are, which are called moles. Okay, so I know the atomic mass of a single, basically, carbon from atom from the periodic table is 12.001. So in this case, when we're doing Avogadro's number, because we're bringing a bunch of them, we may pay attention to the decimal point. We're not just counting how many protons and neutrons are. Okay, we're counting the actual mass, how much they weigh in grams. Okay. So this is 12 AMUs. 12 AMUs, that means that you have to multiply this number by the mass of an AMU, which is something 1.6 or something like that, times 10 to the power negative 27 kilograms. That is for a single atom. For oxygen, again, we're not counting how many protons and how many neutrons, because if I do, they are actually 16. The atomic mass is slightly less in this case. For the carbon, in this case, it was slightly more than their sum, which is 6 plus 6 equal to 12 normally. But we're counting from the periodic table how much the actual mass of the oxygen in this case is, which is going to be 15.99. This number actually takes into account several things. Among other things are the isotopes. Okay. So, so a carbon in this case is 12 AMUs, but 2 oxygens are needed, not just one, to form CO2 in this case. Okay. So in this case, I will need 32 AMUs. So I have to multiply that by how many grams I need. So if I bring 12 grams of carbon, now I know I need 32 grams of oxygen in order for me to form basically the exact amount. When they combine, in this case, is going to be 44 grams of CO2. Okay. So that is basically how many. So if I bring instead 3 grams, then I have to do it in these proportions. Okay, the proportions of 12 over 32. Okay, that is the ratio with which I have to work in order for me to find the exact mass that I need for the oxygen. Obviously, it's a gas, so I have to trap it in here. So Avogadro's number relates the mass of the number of molecules to that of their AMU mass from the periodic table, basically. So from now on, we're going to talk in terms of Avogadro's number. But instead of writing 6.02 times 10 to the power 23, we're going to just write 1 mole to represent the same thing. So 1 mole in this case is 6.02 times 10 to the power 23. For sodium, you need 22.990 of grams of sodium. For lead, you would need 207.2 grams. That is actually the same number as this one for sodium. For helium, all you need is actually 4 grams basically of helium. And in 4 grams, you will have as much as many basically uh, helium basically atoms in this case, because it's an inert gas, that are in actually lead of 207 grams, and they all have the same number. So from now on, we're going to deal with this number, which is called the mole. Okay. So from this point on, that number that is appended and saying, okay, 2 molecules of H2O versus 1 molecule of O2, we're going to deal with the Avogadro's number of them, namely the moles. Okay. So 4 grams now, because I have 2 times 2, which is 4 grams, 4 grams times Avogadro's number. This is actually how many there are in this case. I'm sorry, 2 times 6.02. Forget about this. This is 4 grams, the actual weight. So you need 4 grams, okay? Versus 32 grams of oxygen gives you 36 grams of water, because the water molecules is 18 grams times 2, which is 36 grams. Here is an interesting question. How many moles are in 45.5 grams of chlorine? If you look at the periodic table of the chlorine, it's actually it's the number. It has 17 electrons, but it's actually again, it's the atomic mass in this case is 35.5 or 35.4 to be more accurate. Okay. And again, because as I mentioned before, you include the isotopes, different isotopes in the chlorine, so it's not a whole number. Actually, it's not always a whole number. So it's 35.4 approximate to 35 and a half. So if you multiply that by 2, you're going to find, if I do the math correctly, I have 2 times 30, what is it? 35.4.
Professor, you're muted.
Sorry about that. Not only we were disrupted by the Zoom, I suppose, because this happens with you guys. This is the 4th time I noticed, and it happens only on Tuesday. It doesn't happen on Thursday, and it happens in the morning. So there is something, I don't know what it is, an issue, but I don't know. Okay. So if you do the calculation, the correct number is 0.64, because 45.5 grams, again, the chlorine the AMU for the chlorine from the periodic table is 35.4. You divide 45.5 grams by what is it? 35.4 times 2, which ends up to being 70.8. You're going to get 0.64 moles. So it's slightly more than half a mole. Okay. So for Cl2 again, it's a diatomic gas. So again, that's the correct answer. Did you guys have the chat session? Because I think I lost all of the things that we typed before. So hopefully you guys have it there. Okay, here is an interesting question. How many grams of water are produced from 1.25 moles of methane? How many grams of water that is? So here is the idea. 1 mole of methane gives me 2 moles of water. And 1 mole of water is 18 grams. So 2 moles of water are 36 grams. But I did not bring 1 mole of methane into this equation. I brought 1.25 moles. So 1.25. So if 1 mole give me 2, then 1.25 should give me 2 times 1.25, which is 2.5 moles of water. So 2.5 moles times 18, 2 times 18 is 36 plus half of 18, which is 9. That should give me 45 grams. Does this make sense in terms of a calculation? Because it's going to bring me to the second question of the day. Does this make sense? Okay, very good. Okay, so the question is, how many grams of water we're going to get if we instead brought 1.5 moles of methane? The answer is not listed in there. Can anybody help in here to find the answer? Okay, Naomi thinks it's 54. Can you explain why 54? No. Sherry, I think there are 2 sides to this question. The first one is just 45. You're absolutely right. If I bring 1.25 moles of methane, but the question of the second question of the day is, and it's not listed in here, it's not one of these choices, it's not A, B, or C, or D, is if I bring instead 1.5 moles of methane, okay? And Naomi thinks it's going to be 54. And her rationale is the following. 1.5 basically moles of methane, each 1 mole gives me 2 moles of water. 1.5 will give me 1.5 times 2, which is 3 moles of methane, of water, I'm sorry. 3 moles of methane, 3 times 18 is 54. Okay, I'm gonna do that, sir. But does everybody understand what methane? Sorry, what Naomi has argued? So the question is, how many grams of water produced by 1.5 moles of methane. Does everybody agree with Naomi's argument? She found 54. Let me repeat her answer again, okay? What she said was 1 mole basically of methane. From this equation, you can look at it. 1 mole of methane gives you 2 moles of water. 1 to 2. If I instead bring 1.5 moles of methane, well, the 1 mole will give me 2 still, and the other half mole will give me half of 2, which is 1, for a total of 3 moles now of water. And each mole of water, because water has H2O, it has 16 for oxygen and 2 for hydrogen, 2 times 1, so a total of 18. So 18 times 3 mole, because now I'm getting 3 moles out of the 1.5, so 3 times 18 is 54. Does anybody else agree with Naomi? Because frankly, I personally think she's onto something. I need to see at least one other person to make up my mind too. Come on, guys. Okay, at least another person agreed with her. So now I'm confident too. I think Naomi is correct. Okay, so the correct answer is 54 grams in this case of water, because you brought basically 1.5 moles. So 1.5 moles times 2, that's 3. 3 times 18 should be 54 grams of water. So the correct answer is 54 grams of water, because the question was asking for how many grams of water you will need. Does this make sense? Yes? Everyone else? Okay, very good. I'm glad everybody is on board now. Okay, so that's the second question today. The question now can be put backward. How many moles of carbon dioxide are produced from 50 grams of methane? Okay. Now 50 grams of methane, we have to find exactly how many moles that is. Okay. 50 grams of methane in this case. Of course, first of all, you notice that it's a one-to-one correspondence. 1 mole of CH4 give me 1 mole of CO2. Okay. Now, 1 mole of CH4, C is 12 plus 4, which is makes it 16. So 16 grams per mole. So how many moles in 50 grams? I divide 50 divided by 16. 50 divided by 16 should be 3.125, or roughly 3.13. So there are 3.13 moles of methane. They must give me also 3.13 moles of CO2. In terms of mass, they may not be the same. So 50 grams of methane will not give me 50 grams of CO2. As a matter of fact, it's going to give me, what is it, 3.13 times CO2. And CO2 is 12 plus 6 plus 32, that's 44. 44 times 3.3 over 120 grams of basically CO2. So 50 grams in this case will not give me the same, basically 50 grams of CO2. So in terms of grams, they are not the same, but in terms of mole, there is a one-to-one correspondence in this case. Is this clear? Does this make sense to you guys? Okay, because all I'm interested with is just the moles, so the moles are the same. But if I'm interested in masses, then the issue has to have a little bit more stuff in it. Again, we talked about the reaction rate, the speed with which products from the reactants are basically disappearing, okay? And in this case, we use actually the concentration. So for example, if I have some reactants and see how many they are going, I can say this is the rate of the reaction. I also can rate it in terms of the products, how many products are appearing. So it's the same thing, okay? Because at the same time when reactants are going away, then the products are appearing. So it's the same ratio, okay? So the reaction rate with which product form from reactants is the same thing. It can be affected by concentration. The more of the reactants, the faster they should be, okay? In terms of also temperature, when I'm saying the more, it's more per unit volume, basically. If you put them closer to one another, they should react faster. If you put them very separated from one another, they may take a long time before they reach one another. Okay, that's what concentration in here is. Temperature will enable because a reaction actually will happen when they come very close from one another. As a matter of fact, you can think of it in terms of a collision. Okay, so if they happen to collide in a specific orientation, then they react, and the collision should be powerful enough that it breaks their chemical bonding. Okay, so in order to help them react, you bring them closer to one another. So you increase that concentration. That's one way of doing it. Or you increase the temperature, because when you increase the temperature, they will be moving so fast that there is more chance for them to meet and collide and basically break their bonding and now form new products. So that's another way of doing it. And also catalysts that could help basically bring these two together and make them, first of all, react with it and then break that reaction. So it could help it. And we will see the case of chlorine that it's going to basically destroy, for example, the ozone and make the ozone disintegrate into oxygen. At the end, the ozone, chlorine comes out intact from it. So it's a very bad for the ozone layer in that case. Okay. Again, reactant molecules have to make physical contact with each other in order to transform into new products. Because ultimately, to go back to the previous examples, for example, the methane has to actually be in contact with the oxygen in order for the exchange basically in the rearrangement of the individual molecules, so that you will end up with CO2 on one side and you will end up with water on the other side. Okay. Again, for specific reactions, in this case, you will need really specific orientation for these collisions to help this breaking. In this case, for example, I have, what is it, nitrogen and oxygen. They can combine to give you basically nitrogen monoxide, which is basically an atom of nitrogen, an atom of oxygen. And this has to occur in a specific direction, okay, for that collision to be to result in this chemical reaction, okay. And if it happens at different orientations, it may not result in the same thing, okay. So again, you have two reactants, they come very fast coming to one another, they collide during that collision, they end up now depending on the angle with which they depends on the orientation in this case, okay. They may just basically bounce off, and depending on how they interact. If they are in a head-on collision, like this example in here, you may end up with two different ones, okay. Would you end up with the nitrogen monoxide in this case? A catalyst will help basically in a sense, because first of all, there is an energy, minimum energy, that is going to be needed for the reactants to actually break their bonding. So because they have an energy first of all associated with them, okay. So you need to bridge that gap in order for you to end up with the products that the chemical reaction is supposed to have in this case, okay. So a catalyst could lower, for example, this energy gap. Here is an example with the one I was talking about in this case. Was it the ozone going into O2, which is normal oxygen, and normally the gap is very high, so for the ozone to do that, but in the presence of chlorine, this will make the whole reaction faster. So the chlorine in this case actually will react first with the ozone to form the first of a reaction, and then it's going to react with the ozone again to release the oxygen. So at the end, it's going to be free. Starts free and ends up being free in this chemical reaction. So in this case in here, it's asking carefully examine the following reaction sequence of catalytic formation of ozone O3. So now O3 is being formed from this reaction from molecular oxygen O2. Which chemical is behaving as a catalyst? It's the chemical that appears and disappears at the end. I mean, it's needed first of all to start the chemical reaction, so it's gone in this case. But then it reappears again intact. So at the end, you will have nitrogen monoxide staying intact in this whole thing. So you start with it, it combines with the oxygen. Now you lost it, okay? But then it's going to combine, this product will going to break again and give you two individual oxygen oxygen atoms in this case, which they combine with the oxygen molecules to form O3. So you start with an O2, you end up with O3. And in between, you had an NO, which is really non-existent in this case. Don't talk about then here in this case the nitrogen dioxide, because nitrogen dioxide is not really is a product. Did not exist before. It doesn't exist at the end. Okay, so it was a product, but the NO in this case, nitrogen monoxide, actually was needed to start the chemical reaction, but at the end it was released, so it stays lingering in the same place, ready to facilitate another reaction where the oxygen O2 basically transforms at the end of the day into O3. Okay, so in this case, it's nitrogen monoxide that is acting as a catalyst. How are we doing? We still have time. Okay. So in terms of energy, again, a chemical reaction could end up producing energy in this case. Okay. And this is called an exothermic reaction. Exothermic reaction is a reaction that produces energy versus an endothermic reaction, which actually requires energy for it to happen. So in addition to the reactants, you will need energy for the reaction to occur. Okay. Here is another question of the day. When you burn matches, is that an endo or an exothermic reaction? This is the net, okay? This is the net energy. This is the net energy at the end of the day. Is burning matches an endothermic or exothermic energy? I mean, reaction. What do you guys think? Exothermic, because it gives off heat, but it's not just that. I mean, it's the net energy is actually higher at the end than when you start with. You will need actually to rub the match against the to light it against any surface in there, and that actually requires energy. But at the end of the day, you end up with more. So the answer to it is yes, it's exothermic reaction. Correct? So burning matches is an exothermic. That's an easy way to tell. So that's the third question today. Oh, you want me to type it? Sorry. Is burning matches exo or endothermic reaction? And the answer, of course, is as given by Joshua to be exothermic, because the net in this case is Great. Okay, here is a table that helped me do the calculations. Hydrogen and hydrogen bond has a bonding energy of 436 kilojoules per mole. Okay, and you follow the table in here, for example, hydrogen carbon, hydrogen nitrogen, hydrogen oxygen, hydrogen fluorine, and so on and so forth. Okay, so you do the same thing in here and you follow the table in here, okay, to find the numbers that are needed for this reaction, which ones they are required. And you come and analyze this reaction, for example. In H2 has 436 kilojoules associated with it. In Cl2, I have, where is it? Here, 243. So in this chemical reaction, I have 436 plus 243. That should give me 9, and I have 7, 679 joules, okay? In HCl, again, look at the HCl in this case, and I have 2 of them, by the way, okay? What are we looking at again? HCl. Here, 431, but I have 2 of them, okay? So I have 2 times 431, okay? So 2 times 431, that is in the products, okay? Minus 236 plus 243, that's 600 and something. What is it? I'm going to do the math in here because I'm trying to do the math quickly in my head. So 2 times 431 minus 436 and also 243. Oh. So in order to break this one in here, we needed, I think there's an answer, and the answer is wrong. Exothermic with more than. Yeah, with more than, so it's going to be 183. So it's not exactly 50 kilojoules. It's 100 more than. So the correct answer, yes, it's an exothermic with more than 50 joules. Okay, so I thought it's going to be exactly 50 joules. Okay. Again, this is the calculations I was just doing in here. Hopefully, you guys will go through it. There's calculations in here. So that's the difference between them. So it's 183. That's exactly how much supposed to be. Of course, you have to multiply this number by 2 in here. It's not exactly 431. 431 for each HCl bond. Okay, but you have 2 of them in this case, 2 moles, because that's number is per mole, and you have 2 moles in this case, so you have to multiply it by 2. So this is the energy released, this is the energy absorbed, and there is more energy released than absorbed, and it's more than 50 kilojoules, because when I was looking at it initially, I thought it says 50 kilojoules, but it's more. It's 183 actually, if you do the math quickly. So again, this table is very helpful trying to understand whether or not a chemical reaction is exothermic or an endothermic reaction. Just count how much energy at the end versus how much energy you started with, and you will see how much basically energy is released or needed for the reaction to occur. Again, I mentioned earlier the entropy, and we're not going to get into a lot of calculations with it, but the point being in here is that no chemical reaction is possible without I mean, it has to obey the principles of entropy, which is the second law of thermodynamics. Because there's heat in here, it's still, whenever there is energy exchange, you have to follow the rules in this case, okay? Energy can be released in two different forms, as I said, either directly into terms of radiation in different frequencies, including infrared, which is heat, and also in terms of kinetic energy, where the parts that make up the product basically fly with the tremendous velocity. In this case, that is how the exothermic reaction basically produces energy in this case, and also takes it in similar forms too. So there is more examples in here on how this is occurring actually in the combustion and questions like that. So which one would lead to a greater dispersal of energy? Actually, the exothermic. The endothermic, again, as I said in the introduction, appears to be lowering the entropy, but that's just for the system itself. But when you consider the entire universe, it still obeys the second law of thermodynamics. Okay, I'm going to stop in here because, like I said, we're not going to get into a lot of examples other than these 2 points when you're going to get questions in your questions at the end. Is this points in here related to the entropy? And I'm going to see you guys on Wednesday. I already posted a note from the next chapter. There will be actually, and I know we didn't do quizzes last week, but there will be a quiz this week related especially to this reactions in here because they're important. Okay. So let me stop the recording. Did I say Wednesday? I'm sorry. I meant Thursday. Sorry.